Good evening, everyone, and welcome back to the day two of the AICTE ATAL 6 days online faculty development program on climate change environment organized by the Department of Chemical Engineering, Amal Jyoti College of Engineering, Kanarapalli. Yesterday, we had an enriching start to this journey with insightful sessions from our esteemed speakers. And today, we continue with more thought provoking discussions on climate change and its impact. We have two engaging sessions lined up, delivered by distinguished speakers who bring a wealth of knowledge and experience. Our first session of the day is on the topic Industrial Pollution Impact on Climate Change by respected speaker Dr. Madhuji, FACT Chair Professor. I would like to invite Dr. Suraj Rajan C. to kindly give a brief introduction about our esteemed speaker.
Yeah, good evening, everyone. And today's speaker, first session speaker is Professor Dr. G. Madhu. So, sir is the fact chair professor at the Division of Safety and Fire Engineering, Cochin University of Science and Technology, CUSAT. He has a distinguished career having served as a professor in the School of Engineering at CUSAT from 2004 to 2023. He is also an adjunct professor at the School of Environmental Studies, CUSAT, and BTech in Chemical Engineering from Government Engineering College, Thrissur, and MTech in Chemical Engineering with a specialization in Environmental Engineering from IIT Madras, and PhD in Environmental Engineering from CUSAT. Over 18 years of industrial experience at FACT Limited and former principal of the School of Engineering CUSAT, former Dean of Faculty of Engineering and head of the Division of Safety and Fire Engineering and Division of Chemical Engineering at various periods. He has received Outstanding Chemical Engineering Award from Indian Institute of Chemical Engineers Kochi Regional Center and Professor K.M. Bahauddin Award for Distinguished Engineering Teacher of Kerala, Platinum Jubilee Award from Institution of Engineers Karnataka State Center, and also Young Scientist Award for Ecology and Environment from Government of Kerala. Guided around 36 PhD scholars and currently guiding 14 research scholars, and published around more than 120 papers in international and national journals. And he has presented 70 papers in international and national conferences and granted one Indian patent and completed two major funded research projects. He is the Life Fellow of Institution of Engineers and Institution of Public Health Engineers and the Life Member of the Indian Institute of Chemical Engineers. And SAR has made significant contributions to the field of chemical and safety engineering, both in academia and industry. With all due respect, on behalf of Department of Chemical Engineering, AICTE ATAL FDP, welcome you, sir, to this event. And handing over to you, sir.
Thank you, Dr. Suraj, for the kind introduction. Warm welcome to all the participants of this prestigious faculty development program. The topic of today's first session is industrial pollution impact on climate change. I understand that you had a similar session yesterday also. I think the first session by Dr. Babu Jose should have dealt with some of these aspects, how pollution is influencing climate change. So I will be focusing specifically on the impact of industrial pollution on climate change. We all know that various greenhouse gases are emitted during industrial processes, especially especially from the energy sector as well as from the chemical process industries. So many of the major greenhouse gases are emitted during industrial processes. So I would like to cover the types of greenhouse gas emissions from different types of industrial sources. Then I will focus more on the mitigation of these industrial pollutants, which can lead to global warming and climate change. So this is commonly known to all of us. So the so-called greenhouse effect. Anyway, I'm not going to explain this thing, which is known to you. So since the days of Industrial Revolution, the atmospheric temperature is increasing, and now it has reached an alarming stage. Now, these are the most important greenhouse gases. Uh, of course, carbon dioxide, then methane, nitrous oxide, water vapor, ozone, then a few industrial gases like hydrofluorocarbons, perfluorocarbons, sulfur hexafluoride, and nitrogen trifluoride. All these gases come under the category of greenhouse gases. So if you look at the proportion of the greenhouse gas emissions, you can see that almost 80% of the greenhouse gas emission is contributed by carbon dioxide, followed by methane, which is around 11%. Then nitrous oxide, around 6%, and other gases, HFCs, PFCs, SF6, and NF3, they constitute about 3%. So the major chunk is contributed by carbon dioxide.
Hello, sir.
Dear participants, kindly stay on hold. The session will begin shortly. The speaker will join within a minute, so we kindly request you to stay on hold as we sort things out. Sir, you're not audible. Your mic is
Yeah,
still on mute.
yeah. Now I'm
Okay, sir.
audible, no? Yes,
Yes, sir. Yes, sir.
Yeah, now I'll share the presentation. Is it okay now?
Yes, sir.
Hello?
It is.
Yes, sir.
Yes.
Yeah, I don't know what happened. Yeah, okay. So sorry for the interruption. So this slide you have seen, no? The list of greenhouse gases. Or hello? Am I
Yes, sir.
audible?
Yes,
Yeah,
sir.
Yeah,
yeah.
Yes, sir.
audible, sir.
Okay,
This
okay.
slide, sir.
So
Greenhouse
yeah.
gases
If you have any
slide.
problem, please tell me. Okay. So this is the
Yeah,
list
sure,
of
sir.
greenhouse gases. Then this shows the proportion of greenhouse gas emissions. Carbon dioxide around 80%, methane 11%, nitrous oxide 6%, and all other gases added together almost 3%. Then this shows the greenhouse, that global warming potential of different greenhouse gases. Carbon dioxide 1, methane 28, nitrous oxide 265. It is relative to CO2. Then HFC 23, it has a global warming potential of 12,400. Then perfluorinated compound. Sulfur hexafluoride has a much higher GWP, 23,500. Nitrogen trifluoride is 16,100. But their emission levels are very low. Now coming to the major industrial sources of carbon dioxide. Uh, for example, we all know that thermal power plants, which make use of fossil fuels, which employ fossil fuels, they are the highest contributors of carbon dioxide. Then, of course, the cement plants. Cement plants, they consume large quantity of fossil fuels in their process for the combustion process. Then ammonia plants, especially the ammonia plants without carbon capture. Uh, but such plants are very rare. But in such plants emit a large amount of carbon dioxide. And in most of the ammonia plants are coupled with urea plants, so it is not an issue there. In urea plants, they make use of carbon dioxide to make ammonia. Carbon dioxide and ammonia react together to form urea. Then, of course, another industrial source is limestone calcination. So these are the major sources of carbon dioxide, industrial sources of carbon dioxide. Now, let's examine the case of thermal power plants. So we know that fossil fuels remain the backbone of global power systems, and almost the share is somewhere near 64%, and it has remained unchanged since 2000. Almost 60% share, 60 to 65% share is for fossil fuels. And fossil fuels, we have uh, coal, then naphtha, and natural gas. And compared to coal and naphtha, natural gas is considered as a cleaner fuel. But that also comes under the category of fossil fuels, and of course result in the generation of carbon dioxide during the combustion process. And the fossil fuel generation has increased by 70% since 2000, reaching a new high of around 17,000 terawatt hour in 2018. That the generation of fossil fuel is also going up. So coming to our country, the major chunk of our power generation is from coal. Almost as per this is a statistics from 2017. Almost 56% of our power generation is from coal, which is followed by hydropower 14%, wind 10%, solar 9%, natural gas 7%, then bioenergy and waste 2%, and nuclear also. It is very minimal. It's only 2% of the installed capacity. And by the year 2030, this proportion is slightly going to change. Now we are aiming at reducing the consumption of coal and increasing the non-renewable, increasing the share of renewable sources like solar and wind. So the target is 32% for coal. Solar, we are aiming at a share of 36% by 2030, but we are not sure whether we will be able to achieve this target. And again, followed by wind. The proportion of wind will be almost 17%, and hydropower is also considered as a renewable source of power, but the proportion is it is coming down to, it is expected that its contribution will come down to about 9%. And natural gas, and there is not much change. And this natural gas is also coming down 3% only from 7%, because we are importing all the natural gas, and it is affecting our foreign exchange. So there is a need to increase the generation of renewable sources of energy to meet our increasing energy demands. Now, this is a global comparison of specific CO2 emissions of coal-based power. It is like average CO2 emission in grams per unit. kWh is shown on the y-axis, and it's a comparison between major countries in the world. We are almost, we have our coal-based power plant fleet has the second highest specific emissions of carbon dioxide. It is almost around 1,000 grams per kilowatt hour power generation. Now anyway, we have to think of carbon dioxide mitigation strategies. As engineers, our task is to evolve innovative strategies for the mitigation of all these greenhouse gas emissions. First, we will consider the mitigation strategies for carbon dioxide. So over a period of time, a wide range of mitigation methods have been developed to reduce the emission of carbon dioxide. And there are technological alternatives for reducing CO2 emissions from power plants. So one strategy is switching to less carbon intensive fuel. For example, switching over to natural gas instead of coal. But here there is a problem. We don't have much of natural gas resources, but we have a huge coal resource. So it may not be very wise to increase the share of natural gas in place of coal, because we'll have to spend a large amount of our foreign exchange. Then the second option is increasing the use of renewable sources of energy or nuclear energy. which emits little or no net carbon dioxide. That is one of the preferred options for our country, increasing the generation and use of renewable energy sources like mostly solar. And also now there is again more focus on nuclear energy. But again, as far as nuclear energy plants, nuclear power plants are concerned, the investments are very much on the higher side, and also the safety issues associated. We have to look into the safety aspects. Then the third option is capturing and sequestrating carbon dioxide. That is another technological option for mitigating carbon dioxide. Of course, it's a good option, but there are certain constraints, and we will look into those things. Now, we will discuss in detail the carbon dioxide capture and sequestration, which is popularly known as CCS. It is an efficient strategy to limit climate destabilization due to high levels of energy-related carbon dioxide emissions. So it's a highly promising approach to reducing GHG emissions by capturing the CO2 at the site of the power plant, then transport it to an injection site and sequestrating it for long-term storage in suitable formations. So that is the methodology of carbon capture and sequestration. So first you have to capture it at on site. Then it has to be, that captured CO2 has to be transported to a place where it has to be injected into the storage, long-term storage, and where we sequestrate it. So, installation of it has been found that installation of a CCS unit at thermoelectric plants can efficiently capture about 85 to 95% of the carbon dioxide processed in a capture plant. So we have a very efficient CCS techniques. And again, water is an integral element of many of the CCS processes. So it is used for cooling and also emission scrubbing. So the only problem is deployment of a carbon capture sequestration system will potentially increase the use of water, which will lead to higher withdrawals to meet the added needs for chemical and physical processes. So that requirement is there. So anyway, CCS technology is a viable mitigation option for reducing GHG emissions in fossil fuel power plants. And there are three components in the CCS process. The first component is capturing, as we have already seen, capturing the CO2 arising from combustion, then transporting it to the storage site and storing the CO2 for a long period of time in the storages rather than being emitted to the atmosphere. So these are the three components of the CCS process. First, we will discuss the carbon capture technologies for CO2 capture. Three common technologies are available. We have the post-combustion capture, pre-combustion capture, and oxy-fuel capture technologies. These three common technologies are employed for the capture of carbon dioxide in thermoelectric power plants. So in post-combustion capture, CO2 is separated from the flue gas before they are discharged to the atmosphere. This is a very old process which is employed in, for example, in ammonia plants, which is being employed in ammonia plants for a very long time. And this is the most commonly used method. For example, a solvent like monoethanolamine or diethanolamine, scrubbing of the gaseous stream with monoethanolamine or diethanolamine will remove carbon dioxide from the gaseous stream. So it will absorb the carbon dioxide to the aqueous medium. And the amine solvent is then dried and the CO2 removed. Then that the solvent has to be regenerated. Then that CO2 will be dried and compressed to reduce its volume before transporting it to a safe storage site. So again, it has to be regenerated. That because we have to reuse that solvent, we cannot just discard it. So CO2 is again regenerated. Mostly in ammonia plants, this CO2 is directly sent to the urea plant. That CO2 anyway, CO2 is part of it comes as a part anyway, it will be removed from separated from the synthesis gas, and it is sent to the urea plant. But in thermal power plant, we don't have any such option. So we have to separate it, dry it, and compress before being transported to a safe storage site. Then we have the pre-combustion capture. Before subjecting the fossil fuel to combustion, we can try to capture the carbon dioxide. So the pre-combustion capture of CO2 is based on the ability to gasify all types of fossil fuels with oxygen or air or steam. To any fossil fuel can be gasified, and it can be converted to syngas or fuel gas, comprising of carbon monoxide and hydrogen. That mixture of carbon monoxide and hydrogen is commonly referred to as syngas. And the additional water, steam is then added, and the mixture is passed through a series of catalyst beds for the water gas shift reaction to approach equilibrium, and that will result in the generation of CO2, and which can be separated to leave a hydrogen-rich fuel gas. So that fuel gas can be used for generating power or for other purposes. That is the pre-combustion capture strategy. So this hydrogen obtained from pre-combustion capture can be sent to a turbine to produce electricity, or it can be used in hydrogen fuel cells for transportation vehicles. Here, the pre-combustion capture systems have an advantage. The energy requirement for a pre-combustion capture system is almost half that required in post-combustion capture. That is an advantage. Whereas pre-combustion process requires more water for the water gas shift reaction, because it has to undergo a steam reforming process, and for that purpose we need water. So that is another, again, water is a very valuable natural resource which has to be conserved. So we have to strike a balance between this energy requirement and water requirement. Then you have the oxy-fuel capture process. In oxy-fuel capture, here we use pure oxygen for combustion instead of air, and a flue gas mixture of mainly carbon dioxide and condensable water vapor, which can be separated and cleaned relatively during the compression process. So a separate carbon dioxide absorption system may not be necessary in this case of oxy-fuel capture, because the flue gas mixture will have the mainly carbon dioxide and condensable water. So water vapor can be condensed and removed, and you will get almost carbon dioxide, almost pure carbon dioxide, which can be separated and cleaned easily during the combustion process. So here you can see a comparison between all the three principles of carbon dioxide capture. Here, first you have the post-combustion strategy, where the flue gas is where carbon dioxide is separated from flue gas using a absorption medium. Then you have the pre-combustion strategy, where you get syngas. From syngas, carbon dioxide is separated, and that hydrogen in syngas can go to the power plant. Then in oxycombustion, you need pure oxygen. So you have to separate. You have to obtain oxygen by the air separation process, mostly the air liquefaction process. You should get oxygen, and that pure oxygen is required in oxycombustion process. And the flue gases, which is flue gases after condensing the water vapor, you get carbon dioxide in the pure form, and that can be sent for CO2 dehydration, compression, transport, and storage. Now, this mostly what we practice today is post carbon dioxide capture. That is more popular. So after the carbon dioxide is captured, it gets compressed to a supercritical fluid with properties between that of a gas and a liquid. Then it is transported to a location suitable for long-term storage. And there are many factors which influence the selection of carbon dioxide storage sites. We need a suitable sites. Unfortunately, we don't have much such sites, many such sites in our country. CO2, of course, this discarded coal mines and all, they have the potential to storage CO2, but they have to be developed, and a lot of investment is required to develop such storage sites. So the volume, purity, and rate of the CO2 stream is one factor which influences the selection of storage site. Then, of course, the proximity of the source and the storage sites. Anyway, we cannot have the storage site at a far off place, so they should be close to each other. Then infrastructure, that infrastructure has to be built up for the capture and the delivery of CO2. Then, of course, that existence of groundwater resources has to be considered, because if the water table in the area is very high, that site may not be suitable for developing a storage site. And of course, the safety of the storage site is another area of concern. And of course, several options are available for the storage of CO2. Many popular options are discussed, and some of them are being practiced. For example, injection of CO2 into the ocean. Ocean is a big sink for carbon dioxide. So we can transport the captured CO2 after compression. It can be transported and injected into the ocean so that it gets carried into deep water. That is one option. Or more commonly, by using geological formations as natural reservoirs. Geological formations can be used. Even geological formations in some places, such caves and such storage sites are available. In these areas, wells are drilled and carbon dioxide is injected at depths of more than 1 kilometer. So we have to go almost 1,000 meters down the surface. So that is the method of storing carbon dioxide. Now, another viable option is utilizing carbon dioxide as a renewable feedstock for chemicals. You know that carbon dioxide can be, it's a valuable feedstock for the manufacture of many chemicals. And now this carbon dioxide, now many of these chemicals are obtained from fossil fuel feedstock. Instead of that, the CO2, which is emitted from thermoelectric power plants and other sources can act as a renewable feedstock for the manufacture of chemicals. The reason is that the carbon capture and sequestration methods, they have severe limitations because there are saturation, permanency limits to the capture or sequestration of CO2. Even the storage sites will become saturated over a period of time. There is limitations for injecting limitations on injecting carbon dioxide into oceans and all that. So it is not a very viable option in the long run. So the ultimate solution without hampering the industrial development and urbanization is the utilization of carbon dioxide. So we have to think of efficiently converting carbon dioxide into fuels, chemical feedstock, then even it can be into concrete, household items, and anything that can be consumed in our routine life. So that is a very attractive option, but it's not an easy option. There are many obstacles. We have to overcome those obstacles, but it is a better option compared to capture and carbon capture and sequestration. So we have different methods can be employed for the reduction of carbon dioxide to various products. Basically, we have three types of processes: thermochemical processes, and using thermochemical processes with the support of catalyst, we can make various products like methanol, then propylene, and also urea. Carbamates and urea can be directly produced from carbon dioxide. Then we have the photochemical route where oxide and chalcogenide semiconductors, they act as some kind of a catalyst, photochemical processes. And photochemical processes can be used to generate methane and hydrogen. Methane and from carbon dioxide and water, you can obtain methane and hydrogen, which are very valuable feedstocks for the manufacture of commodity chemicals. Then, of course, we have the electrochemical processes, wherein nanomaterials based on transition metals, alloys, intermetallics, and metal oxides, they are used as catalysts. And these electrochemical processes also will generate the formation of these types of aliphatic acids, carbon monoxide, and methane. So basically, three types of processes. So carbon dioxide reduction, thermochemical, photochemical, and electrochemical pathways. But the choice of catalyst and also the choice of the right technology is very crucial, as it heavily depends on the methods employed. For example, most of these thermochemical reactions take place at very high temperatures, so the catalyst should be able to withstand those high temperatures in a thermochemical reaction. Whereas in a electrochemical method, the catalyst should be able to minimize the competitive hydrogen evolution reaction expected in the electrochemical method. So you had to minimize the competitive hydrogen evolution reaction. Whereas in a photochemical method, you need an appropriate semiconductor with a minimum band gap of 1.23 electron volt, such that minimum band gap is required. And we have to identify an appropriate semiconductor material. Again, considering carbon dioxide reduction, the chosen products of carbon dioxide reduction should have a considerable market size. That is very important. Considerable market size and demand to act as big enough carbon sink. It should have, for example, transportation fuel substituents. The product of CO2 reduction. If it can act as a transportation fuel substituent, then it will be a big carbon sink. And also, if it can act as a chemical feedstock, of course, it will be a carbon sink. So this approach will create an artificial human-maneuvered carbon cycle that will complement the natural cycle to give a sustainable environment. That is the advantage of this carbon dioxide reduction process to generate fuel as well as chemical feedstocks. So, but again, as already pointed out, catalyzing the reduction of carbon dioxide is a big challenge in a chemical process due to the large number of possible products and complicated interconnected reaction pathways. So all these large number of products and the complicated reaction pathways make these chemical processes, the development of such processes, a challenge. And also a viable catalyst. All over the world, a lot of research is being carried out in this area. Even in our countries, many of our national laboratories and institutes of national importance, they are all working in this area. But a viable catalyst is yet to be developed. And again, we have already seen that a large number of products are products are generated during the reduction of carbon dioxide. Almost 17 different chemical or fuel products are generated during the reduction of carbon dioxide. Again, it depends on the material or methods that we employ. So the complexities of the reaction clearly necessitates a rational design approach. Even we have to have a rational design approach for reactors and equipments, and also we should have the ability to scan a sufficiently large chemical space. So this is a list of the 17 products expected during the carbon dioxide reduction process, starting from methanol to propionaldehyde. We have formates, methane, ethylene, ethanol, glycerol, allyl alcohol, acetaldehyde, glycoaldehyde, N-propanol, normal N-propanol, acetone, acetate, carbon monoxide, dimethyl ether, hydroxyacetone, ethylene glycol. These are all major commodity chemicals. All these products can be expected during the carbon dioxide reduction process. So this is a schematic of the overall technology for the efficient conversion of carbon dioxide into methane and other high value products. So you can have what we call you can set up in future chemical process plants may be set up associated with a thermoelectric power plant. The thermoelectric power plant, the carbon dioxide emitted by the thermoelectric power plant can be captured, and it can be directly after compression, it can be sent to the reactor where carbon dioxide is reduced to different products. For example, methanol. Methanol is one of the most important chemicals, and it has a lot of applications. So it's a typical, it's a schematic of the overall technology. So even we can think of a low temperature reaction, but of course we have to do a lot of research and development work in this area. Now, if we consider our Indian scenario, I have already told you that India has vast resources of coal. And if we can utilize that coal, there is a strong economic incentive to meet the rising energy demand. So if we can make use of this coal with capture, even by utilizing the flue gas containing carbon dioxide for manufacture of chemicals or fuel, then it will be an economic, it will be a better economic option compared to the cleaner natural gas imports. So the amount of carbon dioxide emitted from various sectors such as power generation, cement industries, chemical industries, and of course automobiles, it is about 2,100 million tons at the moment per year. It's a annual generation figure. So, but the estimated storage capacity in India, in our country, is only about 4.7 million tons per year, with a significantly higher cost of implementation. So instead of carbon capture and sequestration, we have to think of alternative technologies to maintain growth and increasing living standards while simultaneously managing carbon dioxide emission. So CO2 reduction, if this we have already seen, CO2 reduction technology comprises of 6 parts. First is carbon dioxide capture from coal energy flue stream, which is applicable to our country. A typical Indian scenario, we have coal energy. Coal is used for generating power. So we have to capture that carbon dioxide from flue gas. Then hydrogen production, which is used as the reductant. Of course, here hydrogen, we have to focus more on renewable sources of energy. For example, now we have considerably significant solar power generation, and this solar power can be used for hydrogen production, for splitting water, and by splitting water we can produce hydrogen. So you get that green hydrogen, which is the cleanest among the various forms of hydrogen. Then the third part is the design and development of suitable catalyst. That's an area where we have to focus. Then again, the engineering of the reactor and the process. Then comes the thermochemical carbon dioxide reduction in the reactors and purification of the products depending on the market demand. These are the major components of carbon dioxide reduction technology. So we know that methanol, again, there is enough potential for generating methanol, reducing carbon dioxide to methanol. So we know that methanol is going to be one of the most important products in the Indian energy sector, which is extensively used in a wide varieties of industries like energy, transportation fuel, chemical feedstock, pharmaceuticals, plastics, etc. And our country currently consumes about 2 million tons of methanol, and of which only 20% is domestically produced, and the rest is imported. It is adding to the import bill. So if we can, if we assess the size of the methanol market, the potential of methanol market in our country amounts to around $1 billion, and it is anticipated to grow with the introduction of the methanol economy. So anyway, our government has already taken measures in this direction by mandating the introduction of methanol by blend in gasoline. There are proposals to blend. Already ethanol blending is done. Methanol, I think to some extent, methanol is also blended with gasoline. So here you can see the different processes. This is a summary of the different processes for reducing carbon dioxide into commodity chemicals and final products. So we have different, here again, that second column is that initial conversion. You have electrocatalytic, you can have, think of electrocatalytic, catalytic, plasma process, microalgae cultivation. There is a biotechnological, bioengineering route, then electrobiocatalytic methods. So, and all sorts of primary products can be generated. You can, it's already listed, ethylene, formic acid, methanols. Endo, hello, I'm audible, no?
Yes, sir. Yes, sir.
Yes. Okay. Okay. Thank you. Then microalgae cultivation. From microalgae, you can produce starch, algae oil, and other functional ingredients. And again, from algae, you can again by catalytic process you can think of producing biodiesel and all that, synthetic fuels. Then of course other routes from methanol, all those things. Anyway, there is huge potential for this. It is a promising technology for future. A promising carbon dioxide is a promising feedstock for the chemical process industry. Then from methane, then another major greenhouse gas is methane. It comes next only to carbon dioxide. So methane, we have to deal with the methane gas. So methane to chemicals technologies, they also provide an opportunity to efficiently use this valuable resource. And so a shift to greener carbon dioxide free technologies is often linked with a source of hydrogen, which is an irreplaceable raw material for many products and could be employed as a green, clean energy vector. So the amount of electrical energy for hydrogen production from methane is significantly lower in comparison with the state-of-art water electrolysis. So generating hydrogen from methane, that is again an option. We need hydrogen for future applications. So the energy requirement is lesser in this case compared to the water electrolysis process. So, of course, both technologies produce carbon dioxide-free renewable hydrogen. Then several other processes. So methane is the second most important greenhouse gas after carbon dioxide. But despite its shorter mean atmospheric lifetime, due to its it has a higher global warming potential, almost 28 times that of carbon dioxide. So it accounts for almost 16% of global anthropogenic emissions. So the captured methane usually has, if we cannot use it locally, it is usually flared, leading to again carbon dioxide emissions. So, so processes utilizing carbon dioxide for the production of goods and fuels is an important element of the circular economy. So, so we can even think of converting carbon dioxide to carbon monoxide without any external supply of hydrogen, such as in autothermal co-processing of natural gas with carbon dioxide, because natural gas contains, it's mainly methane. So autothermal co-processing of natural gas with carbon dioxide, it offers substantial potential to avoid GHG emissions from the chemical and refining industry. And this is made possible by providing viable options for carbon dioxide circularity while employing existing local industry. Now, anyway, we will continue our discussion on methane to chemicals. So methane to chemicals, they also contribute to decarbonization of the existing refinery and petrochemical complexes by avoiding CO2 emissions from the flaring of off gases. So instead of flaring methane, we are making use of it as we are trying to make use of it for decarbonization of these refining and petrochemical processes. So it provides solutions for the valorization of these emission streams, and by replacing and by displacing traditional hydrogen production routes of gray or blue hydrogen with a more sustainable one. So this provides such an opportunity also. So here, so this is in here you can see the impact of methane conversion. You have different types of processes are there. So processes wherein we utilize carbon dioxide, and finally we have processes which avoid the generation of carbon dioxide. So impact that methane conversion processes. So CO2 to CO conversion with carbon, for example, that pyrolytic conversion of methane. Then there is we have autothermal co-processing of carbon dioxide in oxidative conversion of methane. Then electrified methane by there is a dry reforming process wherein a mixture of carbon dioxide and methane is used. Then we have methane assisted solid oxide electrolysis process. Anyway, all these processes are under development. So here again, as we go up, the carbon dioxide, the presence of carbon dioxide gets reduced. Then another option is bioproducts from biomethane. Biomethane is now a very it is also a very good option for the manufacture of bioproducts. Then valorization of stranded waste gas streams from the refinery, and electrified production and co-production of renewable hydrogen, wherein we can avoid the generation of carbon dioxide. So anyway, these are the different pathways for methane conversion or decarbonization, represented by the tendency from carbon dioxide avoidance to CO2 utilization. Okay, in a scale from it's a scale from A to G. A is the most efficient, and G is the least desired one. For example, the methane pyrolysis, which is at the bottom. This one, G, is not a preferred option. So methane conversion, it's of particular importance due to its high hydrogen content and availability, including from bioresources. From bioresources also we get methane by the anaerobic fermentation of organic matter. We can generate methane. So of course we can use methane for power generation, and also at the same time it can be a primary source for hydrogen production. So the very popular steam methane reforming. Anyway, it is widely practiced in petroleum refineries and nitrogenous fertilizer plants. This steam reforming process, steam reforming using natural gas, that is the model, is the workhorse for hydrogen production in ammonia and methanol industries and refineries. So natural gas, anyway, if you have a natural gas available, then it can be used very well. So the downside of hydrogen production by SMR, again, it has a disadvantage. Again, there is a significant emission of carbon dioxide. About 11.9 ton CO2 equivalent is produced for CO2 equivalent per ton of hydrogen, which needs to be captured and stored. That disadvantage is there in the conventional steam methane reforming process. So we have to think of a more sustainable process. So the implementation of a process to help the downstream industry with CO2 utilization and provide a supply of low carbon hydrogen is highly desirable. And this represents a paradigm shift where sustainability is the main product and fossil-based chemicals are a carbon sink with significant market value. So there are different approaches for utilizing the excess energy from methane conversion for carbon dioxide. These options include autothermal conversion, electrification with either the production of hydrogen or co-processing with CO2, biomethane feedstock, or the utilization of soft oxidants. So these approaches, so about 4 options, 4 different approaches are there: autothermal conversion, electrification with the production of hydrogen or co-processing with CO2, biomethane, utilization of biomethane feedstock, or the utilization of soft oxidants. So this autothermal conversion process, anyway, many processes are under development, and the main major processes for valorizing methane-rich streams are 2 processes have been developed, and it's almost mature enough. These processes are mature enough for commercialization. Methanol to one category is called the methanol to olefins process, MTO, and the Fischer-Tropsch, that very old Fischer-Tropsch process. So by using synthesized gas and our intermediate, a wide range of products, including light olefins and aromatics, can be accessed in this autothermal conversion. But however, the large amount of intermediate steps, a significantly higher capital investment, and a significant carbon dioxide footprint compared to conventional petrochemistry processes represent significant drawbacks. So therefore, these processes have found the commercial applications in only a few particular regions of the world. But recently, these 2 processes, this methanol to olefins process and Fischer-Tropsch process, they have received significant attention due to their potential for syngas valorization from CO2 enriched feedstocks in a variety of autothermal processes involving methane. Now, there is a renewed interest in these old processes. So the principle of autothermal conversion is based on the utilization of excess energy from methane transformation to drive a second endothermic reaction. That is, that energy can be utilized for CO2 utilization. So these combined processes, so in this combined process, the excess energy is directly used by the second process or is extracted as hydrogen. So it has a lot of potential for future. So it has been initially autothermal reforming has been proposed for low carbon methane to syngas processes as an alternative to steam methane reforming with post combustion capture for hydrogen production. Of course, we have to capture carbon dioxide there. But anyway, the carbon dioxide emissions will be less, will be lower. So in the ATR concept, a portion of the natural gas feed is partially oxidized to generate the heat required to carry out the endothermic reforming reactions. So these are the main desired reactions in this autothermal reactions. Partial oxidation process, that methane oxidation, partial oxidation of methane to carbon monoxide and hydrogen. Then you have the steam methane reforming, wherein you get again carbon monoxide and carbon dioxide. So the first one is an endothermic reaction. A part of the energy required for this steam methane reforming is provided by the partial oxidation process. So regarding hydrogen production, this ATR technology facilitates CO2 capture up to 95% due to the significantly lower concentration of CO2 in flue gases. Then this is a recent development. It is called super dry reforming. A super dry methane reforming reaction for enhanced carbon monoxide production from methane and carbon dioxide has been proposed. Enhanced the CO production from methane and carbon dioxide. So the idea of super dry reforming is based on utilization of the hydrogen produced by a dry reforming process in situ to perform the reverse water gas shift reaction. That's how this super dry reforming process has been developed. So super dry reforming is the first reaction, CO2 plus 1/3 of methane, giving carbon monoxide and water. Then in dry reforming, it is that CO and CH4, they react together to form carbon monoxide and hydrogen. Then anyway, for super dry, all these reforming processes, we need catalysts, and the catalysts comprise of a combination of a classic reforming catalyst. Basically, the classic reforming catalyst is it's a nickel catalyst with a magnesium aluminum oxide base, or with a solid oxygen carrier like Fe2O3 or MgAl2O4, and you need a CO2 sorbent for capture like calcium oxide or aluminum oxide. So the autothermal coupling of these three different processes resulted in a higher carbon dioxide utilization per mole of converted methane compared with the conventional dry reforming process. So the advantage of the super dry reforming process is a lower energy requirement to transform a mole of carbon dioxide to carbon monoxide. It is in fact, it is almost 2.5 times lower, the energy requirement, and which will simplify the reactor design, and it will decrease the energy demand for product purification. Now, of course, this is an emerging option, biomethane feedstock. It's a very important source. Another source of methane that could become a significant point of focus is the fast growing production of biomethane from biogas. So anyway, nowadays, now even compressed biogas projects are coming up in many parts of our country, which makes use of municipal solid waste. The organic fraction of the municipal solid waste can be compressed to, that can be converted to compressed biogas, and from compressed biogas you can generate biomethane. So the proper use of biomethane allows for a significant reduction in the carbon footprint of the energy sector while producing drop-in bioproducts. And again, biomethane could be one of the cost competitive sources for biofuel production, including bioaviation fuel. And this biomethane is produced mainly from non-edible and non-nutritional feedstock, and it remains a concentrated source of renewable energy. So it has this biomethane feedstock holds promise for future. So conversion to fuels or chemicals by electrified methane pyrolysis, it could be an interesting valorization route for biogas. Electrified methane pyrolysis, a process to substitute low efficiency combined heat and power plants in future. And again, this biogas has a carbon dioxide component, that biogenic CO2, that can also be considered as valuable as biomethane in the context of that electrified fuel production. But despite a relatively low production volume, the valorization of biogas will play an important role in the implementation of a decentralized industry. Then another development is the utilization of soft oxidants in the direct and indirect conversion of methane. So in the oxygen-mediated direct conversion routes, the selectivity of this typical OCM process is significantly restricted by the over-oxidation to these COX products and by a significant selectivity to ethane in the C2 fraction. So that is again a disadvantage. Other gaseous reagents like nitrous oxide and sulfur, they have been investigated to a far lesser extent as a milder alternative oxidants to replace oxygen. Anyway, oxygen can be replaced by such milder oxidation agents. So N2O can act as an oxidant. Of course, it is also a greenhouse gas, can act as an oxidant for this organic methane conversion process to form C2 products from the ethane forming reaction. So these are all recent developments. Then again, another route is the halogen mediated conversion processes, because halogen chemistry has played a central role on an industrial scale. And the utilization of a halogen allows the activation of methane at relatively lower, milder conditions, leading to intermediate compounds, which could be readily converted to valuable commodities. Here you can see this halogen route. Halogenated halogens can be used, so you can synthesis of halide compounds of methanol, then electrolysis, and these halides can be converted to lighter olefins. So this is here again, it is the role of gas conversion processes in decarbonization of the downstream industry is shown here. Gas to chemicals, then interface between downstream industry and gas to chemicals, and finally you will get different types of valuable commodity chemicals. Now we will discuss briefly about nitrous oxide. So we have carbon dioxide, then the next the contributor is methane, that is the significant contributor of greenhouse emissions is methane. Then comes nitrous oxide. So these are the different human sources of nitrous oxide. Agriculture is the major source, followed by fossil fuel combustion and industrial processes, then which constitutes about 10%, then biomass burning, atmospheric deposition, of course, the deposition, and human sewage. So they all contribute to the generation of nitrous oxide. Now coming to the industrial sources, our focus is on industrial pollution. So the industrial sources of nitrous oxide, they are unintended byproducts from the production of nitric acid and adipic acid. Nitric acid, you know, they are widely used in the manufacture of nitrogenous fertilizers, explosives, and also it is used for adipic acid. Adipic acid is used in the nylon production and other synthetic nylon, in the production of nylon 6,6, adipic acid is used. So these are the factors that potentially influence N2O generation in adipic acid production and nitric acid production. So the adipic acid, the oxidizing agent, nitric acid oxidation versus hydrogen peroxide oxidation. Then nitrous oxide abatement technologies. We have different processes: thermal destruction, catalytic destruction, recycle to adipic acid, recycle to nitric acid, and so on. Then abatement system utility, that is also very important. Here again, in the case of nitric acid production, the factors are type of facility, then production factors, the catalyst type, catalyst stage, metal gauze, all those things, reactor operating conditions, into nitrous oxide abatement technology. Anyway, you know that nitric acid is produced by the catalytic oxidation of ammonia. So a suitable, we have to select a suitable catalyst, and we have to ensure optimum operating conditions. And it has been found that nitrous oxide generation decreases with increasing gauze temperature and increases with increasing inlet ammonia concentration. Then, of course, you have to select the suitable N2O abatement technology, and of course the NOx abatement technologies. So the manufacturing process of nitric acid, it makes use of nitric acid. Adipic acid is a dicarboxylic acid manufactured by a two-stage process. The first stage of manufacturing involves the oxidation of cyclohexane to form cyclohexanone or cyclohexanol mixture. Then the second stage involves oxidizing this mixture with nitric acid to produce adipic acid. N2O is generated as a byproduct. Then nitric acid production, whereas it involves three distinct chemical reactions. Ammonia, it is ammonia oxidation. Here the first step, mostly nitrous oxide is formed in the first step. That is the main source of nitrous oxide. So we have to think of how to reduce N2O emissions in adipic acid production. Two main techniques have been identified. One is catalytic reduction. In catalytic destruction, a catalyst bed is used to decompose N2O into N2 and oxygen. It's a strongly exothermic reaction, and heat produced must be removed. But the problems associated with the process include the need to recharge a poison catalyst twice a year, and the complex design needed to generate useful steam from the process. Then, then there is another catalytic destruction technique. It involves the use of catalyst to decompose N2O to NO, which can be oxidized and converted to nitric acid. Then N2O emissions from nitric acid, there also we have, anyway, most of the commercial manufacture of nitric acid is based on the oxidation of ammonia. Three main steps: catalytic oxidation of ammonia to nitrogen monoxide, oxidation of nitrogen monoxide to dioxide, and absorption of the nitrogen dioxide in water or other media to produce nitric acid. So the three options exist for reducing N2O emissions in nitric acid manufacture. First is optimizing the nitric acid production process by fine-tuning the process parameters, reducing the N2O emissions using end-of-pipe technologies like catalytic destruction. Then, of course, reducing the demand for nitric acid. So first is optimizing the production process. Production process may be optimized so that the yield of NO is maximized in the first oxidation steps, so that the emission of N2O will be reduced. Then you have non-selective catalytic reduction processes. So the four main methods are there: neutralization with sodium hydroxide solution, extended absorption, then non-selective catalytic reduction. Hydrogen, natural gas, or naphtha react with the NOx and the free oxygen in the tail gas or a platinum or palladium catalyst, and the NOx is reduced to N2. Then selective catalytic reaction. Here ammonia is reacted with the NOx to produce nitrogen and oxygen. It's a high temperature catalytic process. So anyway, I'm not going into the details. We have catalytic reduction of N2O. Noble metals like platinum, palladium, or zeolite catalysts have been shown to reduce N2O emissions by over 80%, and they have been shown to be effective in a process demonstration unit under conditions that occur in the off gases of nitric acid plants. So these are the various mitigation measures, mitigation methods for reducing nitrous oxide emissions. So we have discussed the mitigation strategies for three important greenhouse gases. carbon dioxide, methane, and nitrous oxide. And many of these technologies are under development. Lot of research and development work is to be carried out in this area. And we chemical engineers and engineers from other disciplines can play a major role in fine-tuning this process. Of course, it is a requirement, and in the maybe in the next 10 to 20 years, all these processes. Anyway, we have to reduce the greenhouse gas emission, so we have to take care of carbon dioxide, methane, and also nitrous oxide. So these processes will play a very important role. So with this, I conclude this session. Thank you very much for your patient hearing. And if you need any further clarifications, please feel free to ask. Thank you very much.
Thank you so much, sir. And we now open the floor for questions. Participants, if you have any questions, kindly unmute yourself. You can also type in the question in the chat box.
So I will just close the presentation.
Okay, sir. Are there any questions from the side of the participants? So I hope there are no more questions. I think I would like to invite Dr. Suraj Rajan C for delivering the thank you note.
Thank you, sir, for a very wonderful session for our AICTE ATAL FDP program. It's a very informative session, mainly included how these greenhouse gases contribute to the change of climate, and also have a discussion on how to sequester these greenhouse gases via different strategies. I hope that all the participants get a better understanding about the methodologies to sequester greenhouse gases. And with a token of gratitude, Department of Chemical Engineering, Amaljodi College of Engineering, sharing a virtual memento to you, sir. Thank you so much, sir, for sharing valuable knowledge with us.
Thank you. Thank you very much.
Thank you so much, sir. Thank you so much, sir.
Anyway, and I think I will share that presentation with you. If necessary, it can be shared with the participants also. Okay, so thank you very much.
Thank you, sir. Thank you so much.
Thank you so much, sir, and we are very grateful to have you here as a part of our program. So have